Now we're going to build on the standard cell potential of an electrochemical cell, the E naught of the cell, and we're going to be able to calculate the Gibbs free energy, the delta G naught, as well as K, the equilibrium constant for that particular electrochemical cell. We also need to bring in some new constants. So we're going to be introducing Faraday's constant, which is abbreviated with a capital F. For the most part, the Faraday's constant you need to remember, and the one that you should be writing down in your notes, is 9.684 times 10 to the fourth joules per volt mole. Then we can use it to multiply Faraday's constant by the standard cell potential and the number of electrons used in the electrochemical cell in order to get to the delta G naught, or the Gibbs free energy. Now, for a spontaneous reaction, delta G is going to be less than 0. That means the cell potential must be greater than 0. So you see, we have this double check that we can do with our Gibbs free energy and the spontaneity of our cell. Now we can also relate delta G naught to the equilibrium constant K. And we do that with this expression. Delta G naught is equal to the negative R, remember R is our gas constant, T natural log of K. R in this case is going to be 8.314 joules per K mole. If you're ever given a problem where you're told a temperature that's outside of standard temperature, this is the equation you are likely to need. Now we can combine those two equations into one so that we have the E naught of a cell is equal to, and here we go, E naught of the cell is equal to 0.0592 volts over N. Now the N is the number of electrons used in the overall equation times the regular log, log log, of K. Now this triangle has been shown to help a whole lot of students with what equation to get to what. So you might want to write this down in your notes as well. Now we're going to be applying this to several different types of problems, including this example. So let's calculate what is the standard free energy change. So we're looking for the delta G naught and the equilibrium constant, which we know to be K, for the following reaction at 25 degrees Celsius. Well, the first thing we ought to do is separate this out into our half reactions. We can see that the silver reaction should be multiplied through by 2, and that's what gives us our overall reaction as well. Now we know the iron reaction is the anode and the silver reaction is the cathode. We can look up on our table to find that the anode is 0.447 volts and the cathode standard reduction potential is 0.7996 volts. So we can find the E naught of the cell. Remember, that is found by taking the E naught of the cathode, and we find that on the table, and we subtract the E naught of the anode. Again, find that on the table. And I get a E naught of the cell to be a positive 1.2466 volts. Now I know this is too many significant digits, but I'm going to keep them all in order to avoid rounding error later. Now I can use this E naught of the cell in order to calculate my K value, because I had an equation where the E naught of the cell is equal to 0.0592 volts over N. N is the number of moles of electrons used in the overall equation. So here we needed 2 electrons on either side, Therefore, n is 2. Then I have the log k. Now going to the calculator, I can fill in these numbers. And get the log of k alone, calculate what k is. And then I take the inverse log. When I take the inverse log, I get k by itself, and k is 1.30 times 10 to the 42. Now remember from our equilibrium module that means this particular equilibrium lies very far to the right. We have a heck of a lot more product than we do reactant. So we have calculated k. So now let's calculate our delta G naught. We have another equation. Delta G naught is equal to negative NF E of the cell. So we have our N, and that's 2 because we needed 2 electrons for our overall reaction. We have our Faraday's constant, which you will need to write down and or memorize. 96,480 is what's given. And then we have the E naught of the cell. Again, I didn't round it on purpose. And then we do our multiplication. When I multiply this all together, I get a negative 244, and the units here are going to be joules per mole. Now, because this is a large number and we're talking about a delta G naught, we usually talk about delta G's in kilojoules per mole. So I'm going to round this as such. Now we did start with 3 sig figs here, but because they were provided for us, they aren't exactly measured. It's difficult to say how many sig figs that we would have. Now, I'm not going to be very particular about your significant digits in a situation like this. This is obviously too many. You shouldn't report something like this, but 3 or 4 significant digits should work. Now we can calculate our K, but remember the relationship between Q and K, and we talked about this with our equilibrium unit. So Q is the reaction quotient. And if we exchange Q for K, then we can calculate at non-standard conditions as well. In order to do that, we need to have the non-standard E cell is equal to the standard E cell minus 0.0592 volts over the number of electrons times the log base 10 of Q, the reaction quotient. And we can do that with an example like this. If we consider this reaction at room temperature, is the process spontaneous? Well, like other problems that we've worked, first we'll work out the half reactions. This is my anode. And here is my cathode. Now we need 2 electrons to make this reaction occur, so N is going to be equal to 2. Now looking up the values, the standard reduction potential values, my anode standard reduction potential is negative 0.28 volts, and my cathode 0.447 volts. So the E naught of the cell being the standard reduction potential of the cathode minus the standard reduction potential of the anode, and I get a negative 0.167. Now I know this is too many significant digits because of this value here is reported with only 2 sig figs past the decimal place. I'm going to keep it to avoid rounding error. So now I can use my non-standard conditions, and I can find the E of the cell, the non-standard cell. Now I start with the E0 of the cell, the standard cell, and I will subtract this non-standard adjustment factor. Now the log of the Q, remember that's going to be our products over reactants. So if I fill in my numbers here, the negative 0.167 is what we calculated right here, 0.0592 volts. That's what happens when we work out with our constants. 2 is how many electrons we used in our overall reaction. Then we'll take the natural log of the reaction quotient Q. I'm going to take my product, the molarity of my product, and divide it by the molarity of my reactant. And in the calculator, you should get a negative 0.137 volts. Now, in standard conditions, this is a non-spontaneous cell, and it's non-spontaneous because the the E0 of the cell is negative. Remember, a positive E0 indicates a spontaneous cell. So at these conditions, this is still non-spontaneous. Finally, we have our concentration cells. So what's the cell potential of this concentration cell? Now, a concentration cell looks like there should be no net reaction because you have the same cathode and anode, and they're reacting to form the same cation. But what we have is a difference in concentration, and that makes all the difference in the world. So first thing I'm going to do is I'm going to peel out my half reactions. I have my anode reaction. And I'm just going to put that concentration right here. And this is my anode. And the standard cell potential for the anode, standard reduction potential, negative 0.7618 volts. And then I have my cathode. I'm going to put that concentration just below it just to keep track. And that reduces to form the solid zinc, and that is the cathode. And the cathode standard reduction potential is 0.7618 volts. So you see the standard cell potential, the expected standard cell potential for this cell is 0.7618 minus a negative 0.7618. So at standard conditions, be 0. But we don't have standard conditions, and that's why we have to do the calculation. So now we take the E of the cell is equal to, we start with the standard cell potential, and then we adjust it. We adjust it with our non-standard conditions. So the E0 of the cell minus, there we go, 0.0592 divided by N, which is the number of electrons used. So we would have 2 electrons that need to be transferred, times the log of Q. Now remember, Q, the reaction quotient, is going to be products. So in this case, we're going to have our products over reactants. So before I go making any more mistakes, let's work out that final equation. I'm going to change my colors here, try to make it stand out. So the net reaction, we would have 2 electrons on either side, so they would cancel out. Our solid zinc is going to cancel out. So our net reaction is actually going to be this zinc forming this zinc. Therefore, for products over reactants, our product has a concentration of 0.10 capital M molar, and our reactants have 0.50 molar. So now we can put this in the calculator and end up with a positive 0.0207 volts, we have two measured quantities here, and those two measured quantities have two significant digits, so we would report two significant digits. This is a spontaneous reaction, and it is spontaneous because the E of the cell is greater than 0. It's positive.